What I'm about to show you is possibly the biggest project I have ever embarked on as a programmer. I've done other small things in between, but this is what I've really invested my hours in. I faced many challenges along the way and accomplished many things, and in fact, it's not even finished yet. You see, this is Orion, a humanoid home assistant that can autonomously navigate to any room in my house and which has an AI-based brain that allows it to converse, look things up, follow orders, and even detect who's talking to it. And hopefully, soon it'll be able to cook, clean, iron clothes, and so much more. The reason why I'm making this video before giving it arms to do all the useful stuff is that that's gonna open up such a huge rabbit hole that I just wanted to record what I've done so far and how I've managed to do it. So, without further ado, let's start from the beginning. It all started back in 2023, when my dad showed me a piece of news about robot butlers in hotels or something. I don't know if it was this exact model, but it showed a robot very similar to this one. Now, of course, I had always liked robotics, and I already knew to code in Arduino and had made some cool little projects, which, needless to say, didn't even come close to the complexity of a full-fledged home assistant. However, I suddenly got the alluring thought of, hey, why don't I make one? Naive? Perhaps, but that thought soon grew in power, to the point where I found myself researching exactly how I could make a fully capable humanoid robot. In that research, I discovered the Raspberry Pi, a single-board computer, or SBC, widely used in robotics and DIY due to its convenience, support, and affordability. And I just went and bought one. I also got a LiDAR for Christmas, which is basically a sensor that sends thousands of infrared beams in all directions to measure the distance to each point and get an idea of the shape of its surroundings. And only then did I begin to realize I had no idea where to even start and looked up a tutorial. My searches led me to conclude that my best bet was to try and set up ROS, or Robot Operating System. It is used all around the world in all kinds of robots and has an active community, which would prove useful should any troubles arise. The first thing I wanted to set up was my robot's autonomous navigation system, which implied localization by using the aforementioned LiDAR to kind of match the surrounding shape to an actual location. Now, I'll be honest, there are few actually good tutorials on ROS, but I found one by Kevin McAleer, and even though I didn't use it in the end, both because of better options and unsuitable follow-up, it very much set me on the right track. The first thing I had to do was set up my Raspberry Pi with an operating system. The tutorial used Ubuntu 2004. Now, I don't know what exactly I did wrong, but I booted to no desktop. I also had so much trouble setting up the Wi-Fi, and when I finally managed to get something resembling a desktop, it had no apps. No browser, no terminal, nothing. Just a background. Great. I ended up having to manually install everything and set up the GNOME environment myself. Not without constantly running into all kinds of errors, of course, and then I could finally begin the actual tutorial. I was quite quick to install ROS Noetic and set it up, but then my LiDAR turned out not to work for some reason. And after more than a month of scouring the internet, I came upon and installed the correct package for my LiDAR, which is a YD LiDAR instead of the tutorial's RP LiDAR. I was extremely confused because I hadn't anticipated having to do things differently than what was literally shown to work in the video. Anyway, I finally managed to get a scan of my surroundings. The next thing I needed was an actual package to use that LiDAR data for navigation. However, the tutorial ended there, so I was again on my own. I found Hector SLAM, but then went with Gmapping, which are alternatives to the default SLAM package. SLAM simply stands for Simultaneous Localization and Mapping, so pretty useful stuff. I don't know why I went with that instead of the default SLAM, which in my opinion is better, but I started following an online tutorial to set it up in simulation. Then I tried to make a map with the real data, and boy did that give me trouble. First I forgotten to deactivate simulated time, then I had transform errors between the ROS topics, which are some of the most annoying errors you can get in ROS. And then, once I finally managed to get my LiDAR to produce a map of my room, which I could potentially use for navigation, it turned out it wasn't giving me odometry data, basically data about the robot's position, and I went back to Hector SLAM. However, I managed to solve the errors that gave me quite quickly, and finally had a map and the software that figured out the location of my LiDAR. Now, up to this point, I'd been a bit in and out of this project with little idea how to continue. But this is where I really locked in and things got serious. I followed what's in my opinion the best tutorial series on ROS out there, or more specifically ROS 2, the videos on articulated robotics by Josh Newens. It was a whole different operating system and environment, which meant I had to basically restart from scratch, but now I knew how stuff worked a bit better. I wouldn't make the same dumb mistakes as before. I again had a lot of trouble setting up Ubuntu, now Ubuntu Mate, mostly because it was basically deprecated at that point, but I managed to slowly but surely follow the tutorials. Always with more errors than the guy, because of course, but I was able to run a simulated version of my robot which worked perfectly. And then I came to the conclusion, it was hardware time. Time to make the same transition from simulation to reality that I'd done before. But now, I'd do it right. To test navigation, I didn't really need to overcomplicate things and make the thing human height. All I needed was a base. I wanted to make it fairly heavy, as otherwise such a tall robot would become unstable, so I just grabbed a wooden door from the nearest garbage container and got it into 2 boards. Yeah. I also bought some 12-volt high-torque motors and some Pololu motor drivers, which I would later need to replace with a good old L298N due to how painfully incompatible they were with the tutorial. The L298N driver can only manage 2 wheels. However, I realized I could just control both left wheels and both right wheels with the exact same commands and they'd work. So I designed some wheels, optimized for structural integrity, which I 3D printed, bought a 30 amp hour battery, and my temporary setup was ready. Here I reached the part of the tutorial series where it was time to get the wheels moving. Although as the simulated and real robots files are really similar, the jump from this to getting a working robot was basically instantaneous. However, I had a problem. The package Josh Newens provided for controlling the robot's motors was supposed to work with this kind of robot, one with 2 rear wheels and 1 caster wheel. But my robot had 4 wheels to control. Now I know I said I could control them both with the same signal, but I still needed my code to acknowledge their existence, so I couldn't just act as if they weren't there. And in an absolute pro hacker move, of which I was very proud at the time, I modified the package's source code to simultaneously keep in mind 4 wheels, but only send actual hardware signals to 2, which was pretty hard to pull off, but I managed in the end. And then it turned out I had to modify the source code again because I wasn't using encoders. You see, normally, motors used in robotics have encoders attached to them, which are little components you can use to tell exactly how much a motor has rotated, which is important so the robot knows what it's doing. This is called a closed loop system. But I didn't have encoders, so I needed an open loop setup, where the robot calculates its wheel states based on the commands it sends to them. However, this was just not supported by the tutorials package, and there didn't seem to be any alternative this time. So I had to modify the entire thing, bypass PID calculations, and implement my own system for sending signals to the motors. And it worked! I spent a while trying to get SLAM to work, but I finally got it right and it was time to map my house. However, if this was going to be my final map, I needed to place the LiDAR in its final position. As it could not be blocked by anything on any angle, that meant on top of its head. Now, I didn't have too much of an idea how I was going to make the torso, so I just bought the metal bar I was going to use for the central structure and temporarily attached the head I designed on Tinkercad on top, and we'll get to it later. Once that was done, I could finally make a map of my house. Well, that's easier said than done because some of my rooms are quite similar and my robot went, "Oh, I've traveled all the way here from the kitchen, but this sure looks like the kitchen. Let me just teleport my position estimation back there and mess up the whole map so you have to start all over again." Yeah, that happened too many times. But after a long while, I finally had a map I could use. Now, it was time for navigation. I used the most popular package, and the one explained by Josh's tutorial, nav2. However, there was still one thing left to do, because as my LiDAR is so high up, it can't detect much of the furniture my robot could bump into, so I needed to set keep out zones for nav2 to follow. And would you have it, keep out zones are not available in the ROS 2 Foxy version of nav2, so I needed to switch to ROS 2 Humble, a newer version, except that meant I also needed to change my Ubuntu version, so I had to start all over again. Luckily, I reached the point where I was before quite quickly, as the files were almost identical between the two versions. It also turned out I couldn't use Gazebo anymore, the program I'd been using to simulate, because it wasn't compatible with Ubuntu 20.04 on ARM64, the architecture the Raspberry Pi uses. Although I wasn't really interested in simulation anymore, so that was fine. Anyway, I finally added a map of keep out zones on top of my normal map, and now my robot was ready to follow it. It was amazing to finally see my robot actually do something by itself. Nonetheless, what happened most of the time was more similar to this. The root cause of this ended up being CPU load, so I used composition mode when launching the nav2 stack and also tweaked many of the hundreds of parameters there are to optimize navigation. So once my robot was able to go from any room to any other room by itself reliably, I determined the best thing to do next was to give my robot its brain. My head was designed to include a microphone, so the robot could hear, a speaker, so the robot could talk, a camera, so the robot could see, and a gas sensor, so the robot could smell. I decided to start with the speaking part, so I got a Raspberry Pi 5, a microphone, and a speaker, and started coding. Of course, I wanted to use the current state-of-the-art in LLMs, a GPT model. Now, I had three main options. Use a trash open source GPT, which would absolutely overload my poor Pi, use OpenAI's API and pay actual money for talking with my robot, or make a script to emulate normal user interaction with the actual ChatGPT. Yeah, that sounds much better. So I made a Python script that used Pico Voice Porcupine to detect a wake word and then Google Speech Recognition AI model to recognize what it's being told. Then I used PyAuto GUI to write the recognized words onto the text box in ChatGPT's UI, detect when it's finished responding, copy the text generated by ChatGPT and return it to the script. And finally, I used Piper, a text-to-speech module, to turn ChatGPT's output into, well, speech. And in effect, that meant my robot could now listen and respond to anything in natural speech. Well, kind of. The thing is, Piper uses eSpeak, the default Linux TTS model, which sounds a bit kind of like this.
If I wake up at night and hear this voice greeting me, I think my soul will leave my body.
Yeah, not great. So I decided to exploit ChatGPT itself further by just using its built-in TTS function.
Hi YouTube! Hope you're having an awesome day. What are we building or exploring today?
Yeah, that sounds much better. While doing this, it occurred to me that my robot had no name. And what better way to choose one than to let its AI choose it itself? As you might have guessed, it chose Orion. So I made that the official name of my robot and set that as the wake word. But now I needed Orion to recognize orders from speech. And now that we're using a whole GPT, why stick with formulated ones? I made custom instructions on ChatGPT so that it would print certain quiet strings of text along with the sensor if it recognized it had been told to do something it could do. Then, if my script detected those strings in the answer, it would publish a specific message to an MQTT server. Now I needed to set up the gas sensor. I used an I2C analog to digital converter module, as the Raspberry Pi doesn't support analog input in its GPIO pins, to take the measurement from the sensors, turn them into values, and make the robot express its concern about the air quality if the concentration of hazardous gases was too high.
The air quality here is dangerous.
And in that same script, I wanted to add a function to read my battery's voltage, because the voltage tells you how full it is, so that the robot could know if it was time for charging. I took an end of my divider cable, set up a voltage divider to pull down the voltage to about 3 volts, and connected that directly to my ADC. Then I made a rough calculation for the battery percentage and made the script publish that to my MQTT server. So I set up a listener for that server on the robot's base and used the basic navigator to send goal positions to nav2. Now, if I verbally told my robot to come to my room, it would. But then I thought the thing about telling it to come is that it's not here, right? So I made an Android app. I downloaded Android Studio and quickly picked up the basics. The app was quite simple, with just a few buttons for the different actions and a client for the MQTT server to publish commands to one of the server's topics and read stuff like the battery percentage, which the app displays. And I also took this opportunity to make good use of the camera slot by adding an RC mode. I set up Media MTX in the brain to read the input from my Raspberry Pi camera module which I had attached as the eye and publish it through RTSP. Then, when you go into the RC mode menu in the app, it subscribes to that server, displays the image, and lets you send raw movement commands to the robot through some arrow buttons. In the Basis Listener, I added a way to switch back and forth between RC and normal mode, and now I could seamlessly take over the robot's normal functions and drive it around. I even added a microphone button so that I could record my voice from my phone and talk to others in the house remotely through my robot. Which was honestly a bit of a nightmare to get working because Media MTX and the ChatGPT script kept fighting over ownership over my microphone. Just Linux sometimes. So next up, as a final test for my NAV2 setup, I decided to try and dock my robot to a charging station, which would require the utmost reliability and precision. Of course, to do that, I needed a torso for my robot. Now, I didn't yet know how I was going to make the arms, so I just added some generic holes on the side. After nailing a beautiful design with my logo elegantly imprinted on the lid, I divided it up for printing and made the longest prints I've ever done. I actually tested some new techniques in the process, like the trick of adding hairspray to the bed to make prints stick, and using tree supports instead of the normal ones. And now I can say those are some really good tricks. Once I had assembled the torso, I placed it on my robot and it fit like a charm. I also placed the battery inside with its input cable in the hole in its back, added some screws for the lid, and now this is starting to look like a real robot. While the torso was printing, I had designed a charging station to use as little plastic as possible, because at that point, hearing the printer all day was driving me insane, to later reinforce it with other materials. So now I could print that, I attached it to my wall and reinforced it, and it was time to make the robot navigate to it. I made a special function in my listener script, which was more of a manager than a listener at this point, which navigated the robot to the correct position and then made it move backwards to dock. However, I ran into two problems. First, the robot was a bit heavy, and when the battery was low and it made a sudden movement, the motors drew so much current that the Raspberry Pi turned off. And second, when the robot finally reached the goal, it gave me a weird non-rotation error and never actually finished aligning with it. The cause of the latter turned out to be that I had set a minimum linear velocity to avoid stalling the motors, but that meant it couldn't complete movements that only required rotational velocity. It took a while to pinpoint that out of the hundreds of parameters, and I even optimized some other parameters in the process of researching, but once I had solved that, my robot finally docked to the charging station. So I set the home position to that, added the wake up and go to sleep functions in my app, put all the scripts into systemctl all services so they would launch automatically when my Raspberry Pi is turned on, and now my robot could autonomously charge itself when its battery was low and be commanded to dock or undock as needed. So yeah, after all this journey, now that the autonomous traveling is all sorted out, what's left is to give Orion some actual use. And that'll mean giving it arms. I've actually already ordered the motors, and I am planning to control them with the Move It 2 package for ROS 2. This has been such a cool project so far, and hopefully soon I'll have a robot making dinner for me. Until then, thanks for watching, and I'll see you next time.